we are cynical. We start saying, hey, this thing is not going to work. This thing is not going to work. We try to see the faults with that. That happened with pre-stressed concrete also. And you see where pre-stressed concrete took us right now. We are able to build robust beams, robust bridges, robust structures, much higher strengths. I mean, we are able to avoid crack-free structures. I mean, there may be some problems with pre-stressed structures. We can, well, but the if you see change the horizon, if you pick structures nowadays, you will probably see 50, 60, 70% of the structures as pre-stressed concrete and 20 to 30% as reinforced concrete. In the United States, where I am working, ours is a precast manufacturing facility in the backyard. So we do like 80, 90% of the structures of pre-stressed concrete, actually. Pre-stressed concrete. The number of members that go out of the factory at the end of the day that are designed using reinforced concrete is not even 10% these days. Not even 10%. They are phenomenal, like so many advantages. Similarly, the reason I'm talking about pre-stressed concrete is how much transformation we had when we are switching from RCC, reinforced concrete, mild steel designs, to pre-stressed. The same thing, the same kind of transformation is going to happen. I mean, this is a prophecy. So we can come back after 10 years and see, hey, Srimaruthi garu, you said that thing on that day, you said this thing, but it's not going to happen. And I'm sure it's going to happen in 10 years or 20 years or maybe more, when we drift away from probably the pre-stressed concrete and go towards ultra high performance concrete, or at least a hybrid of pre-stressed and ultra high performance. This is going to happen. That is why I had this vision for UHPC. I saw where it is can take us. So I started investing some time on ultra high performance concrete. Now, please stop me if you want to add something to this discussion. Otherwise, I'll go a little bit quickly into the presentation. I'll try to avoid some visuals basically, which do not help much, except for the presentation's sake. I'll invest more time into the discussion rather. So that's just a bridge that you are seeing, a pedestrian bridge in Canada that was built in 1997 using UHPC. Canada is actually a little ahead of the United States, even in UHPC. So we're going to see what is UHPC, how did it evolve, what are its properties, I mean, a little discussion on design philosophies and applications and conclusions. Okay. So it's often referred as UHPC, which stands for ultra high performance concrete. That's what UHPC is essentially. But when I was reading the literature, when I was doing research on that, and I was reading the books, and I was reading the research that has been done so far, I understood one thing. Actually, UHPC is not a formula that, hey, this is this. I put this. This is UHPC. There is no such thing. You cannot say that. A lot of research has been done on producing high strength cements. It dates back to French research labs, actually. Okay, French research labs, where they were trying to get really high strength cement mortar, basically. So they were trying to get cement mortars, and they realized that one big thing they found that was, if you can pack the materials very densely, dense packing of the material is probably going to take us to higher strengths, higher properties. So they called it ultra, what you call high strength cements. They used to call high strength cements. Then eventually, the initial concretes that were made using this formula that gave them high strength cements, they started calling it, high strength concrete. Eventually, it became high performance concrete. Then it became some people added fibers to that, and then it became fiber reinforced concrete, high strength fiber reinforced concrete. You'll see so many different words for this one, essentially, that have been used in the past. And ultra high performance concrete is one word that has been, uh, you know, that has been like kind of summarizing its performance, all those things. So you still, in some parts of the world, you may see it as ultra performance concrete, high performance concrete also. So yeah, the words are, keeping the words aside, keeping the abbreviation aside, basically what does it stand for? It's very high compressive strength that provides high performance in terms of durability, in terms of impact resistance, fatigue resistance, crack resistance, high, very impervious, very low permeability to chloride ingress, or say sulfate ingress, moisture ingress, all these things. Okay, that's, I mean, anything, any material that gives you these properties can be called, and that is made of concrete, of course, that is made of aggregate, water, and cement. Obviously, is called, you can call it UHPC. So this is the statement I was trying to basically emphasize. It's very relatively very new material. I mean, what is new in research, or what is new in civil engineering? What is new in civil? Something that is 20 years back, 30 years back, is not old basically. Something, an idea that started 30 years back is not old at all. It's considered new, even though it's 30 years back, basically, in French labs. Okay, so the reason is, again, the reason is same, because we are scientists. We want everything scientific. We want everything to be proved, and of course, that's the job of some of us as researchers. That is the job of the researchers, to basically bring a new idea, test it out, verify the results, see its applications in different areas, see how it is performing, see what are the problems, identify the problems, and then try to come out with solutions that mitigate, and eventually produce a product, or produce a concrete that is a lot better than what we are doing right now, and see if it works in the long term. That's the researcher's job. And then the engineers, the industry basically takes it out, and then they implement it on a large scale. That's how it works. There is a huge gap in between these two. It takes significantly long, like many years. Pre-stressing, we started like probably in the last 10-20 years, right? That's all. But pre-stressing, when was pre-stressing actually proposed? 1950s, or no, around 1950s, probably, in French, again by French people, pre-stressing. Uh, it takes like 40 to 50 years for the people not only to test, implement, and verify it, but also to overcome the stigma, basically, overcome the stigmas of accepting superior things that are new, because we don't know them. We have that stigma that it takes very long time. So little research has been done. I'm not sure how much research is being done in India on this one. The real, genuine real research, not just like, verifying already that it has been verified somewhere else, is different. But coming up with something new, testing, what you call very authentically, within the country, doing our own verifications, doing our own research. I'm not sure. I cannot speak on that one, but that's something we have a lot to work on. And implementation is in practice around very few countries in the world, obviously. So again, this is only what I was talking. This particular slide summarizes a little bit of what I was talking, how construction industry reacts, why it takes time. You know, of course, UHPC has gained prominence in Asian countries. I think South Korea, China, Malaysia, Japan. These countries are going forward, as compared to even European countries or United States. Of course, United States is not that forward on UHPC. No, I'm guessing. Okay, yeah. Uh, So this is again, this slide is just talking what I already spoke. What was considered M50, achieving M50 was a challenge few decades ago, but now we are already talking M125. Technically, ACI, as per American Concrete Institute definition, um, I mean, for a concrete to be called ultra high performance, uh, the around M120, basically I converted the units. Okay, M120 is probably 12 14s, 48 of this, yeah, 40, probably close to 20,000 psi. Okay, which is 120 M120 grade. That's where you are technically calling it UHPC. You can technically call it UHPC. Otherwise, it's not UHPC. It's probably not traditional concrete. Traditional concrete definitions end around M50, M60. So you're falling in that zone between traditional concrete and UHPC concrete, between M60 and M120. So coming to, I mean, this is evolution. We can skip this. We all know, many of us know how we are at a point where we are talking about UHPC, and then some of these things. Yeah. So common ingredients. Okay, we all know cement, we all know sand, all these things, water reducing mixtures. I think we have been using silica fume also in some mixes. Obviously, Silica fume is commonly used to enhance the strength of the concrete and the properties of the concrete. Even mixes that use M40, M50 also use silica fume. And then something interesting is quartz floor here. Quartz floor, it says. Okay, quartz floor. That's the important point right there. When we see here, so quartz floor. So you might be surprised that there is not much of there is something missing here. Can anybody notice what it is? If you see this thing, common ingredients: Portland cement, fine sand, silica fume, quartz floor, water reducer, steel, fibers. What is missing here, essentially, from a traditional concrete?
Aggregates?
Yeah, the coarse aggregate. Yes, coarse aggregate. If you see coarse aggregate is actually, you don't see coarse aggregate here, essentially. So, I mean, it's not a formula I'm saying, but this is the most common thing. This is the most commonly seen, one of the commonly seen mixtures for UHPC. So coarse aggregate is missing. So that thing caught my attention actually. Oh, why are we missing coarse aggregate? Why is coarse aggregate? Is it not added every time? I don't say that statement that it cannot be added, but at the same time, adding a coarse aggregate actually, you know, can potentially reduce the density. How good the pack is, how good the pack is consolidated into one piece. Okay, when you put all these materials together, you know, it's like this. We all use dough at home, right? For chapati, for example, we make dough for chapatis, to make chapatis at home. So when we mix the dough when we mix the dough in a dough, all the ingredients are extremely fine. Essentially, actually, if you see the flour, you have flour and water basically. You have flour and water. If we put some sugar crystals or something inside. Let us say if we add sugar crystals, each crystal is slightly bigger. Okay, sugar crystals, we know, right? We just eat at the temple. Sometimes they offer it as prasadam at temple, sugar crystals. So if we add some sugar crystals into chapati flour and mix some water into that one, and then you feel it when you actually make the chapati, you just get some dents in the you get dents in the in the chapati, right? In the mold, when you're actually making it with, or pizza, whatever it is, and you're rolling it with the stick, you get dents into that, obviously, because your crystals, sugar crystals, are actually poking holes into your flour. Okay, I don't know, flour is soft, so you get poked, so it is poked. But obviously, the point here is the moment you are adding crystals to the dough is no more uniform actually. Until now, it was very uniform because it only had flour and water. Pindi, I mean, sorry, yeah, flour and water. It only had a flour and water. Now it has flour, water, and crystals. The crystals are in. Actually, the crystals are themselves strong. The crystals may be themselves strong. The aggregate itself may be strong, but the addition of aggregate is actually reducing the density, the homogeneity. Homogeneity is very very important in a mix. For that point, because homogeneity is what is bringing the density, and that is what is bringing the strength, that is what is bringing the impermeability, that is what is making this mix robust, essentially. That is what is actually keeping it together, not allowing, hey, I'm not allowing water to get inside me. I'm not allowing, I mean, of course, when you cut down the water coming inside, you're cutting down chlorides, you're cutting down sulfates, you're cutting down everything that is coming along with water. Even corrosion, obviously, the cut basically path for corrosion completely. So these are all the advantages that come with homogeneity. The secret to HPC is homogeneity, essentially. That's one thing that I understood reading about this material. Okay, that's the reason we don't probably see, are not probably seeing coarse aggregate in this mix. Now, another very 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 important factor is this thing, the bolden line. I boldened here something, emboldened something here, which is the water cement ratio is less than 0.25. This is, I mean, this is very very interesting. Such a low water cement ratio. All our life, when we are learning about uh, conventional concrete in our classroom, in our experiences, in our jobs, we were always listening the counter of it. Actually, if you look at this point, we were always taught the counter of this one. Hey, water cement ratio, low water cement ratio is good for strength. Okay, we know that. What our textbooks always said, go to any standard textbook like MS Shetty or concrete technology. We have been taught all the time, we have been always thinking, our experts were always thinking that, you know Low water cement ratio is good for strength, but we can't achieve it because there are a lot of problems with that. And we don't want to achieve it because low water in the cement actually can give a lot of problems with curing of concrete. That's why we are curing them so much, right? Once concrete hardens, we add water to the structure constantly to keep the heat of hydration low. Otherwise, several cracks will come. And that's number two, not even number one. Number one is if there is not enough of water in the concrete, your concrete doesn't gain strength at all. That's what we have been always trained. That's why we keep our water cement ratios in conventional concrete 0.4, 0.45, zero point 0.5. Even in the regular mixes of M25, we probably use 0.5 water cement ratios. Because we are afraid if we put less water, if we put less water, there is not enough water for hydration. And when cement doesn't have enough water for hydration, it doesn't get enough strength. Uh, is anybody trying to say something? I can't hear. Uh, I can see. I can see Dr. Naidu garu trying to talk something. I think does he have any question or?
Yes, sir. Regarding the high performance concrete, actually, the people, uh, a few people understand.
Yes,
Few
yes,
people
sir.
understand. Only few people understand the difference between high strength concrete and high performance concrete. That is the question of the discussion of the present day.
Hmm.
High performance is regarding the durability and all those things, mechanical properties and durability properties more
Hmm.
regarding the environmental effect or density, less weights or porosity and all those things, and more dense. High strength is different from this thing. So people are to be very aware, shall be aware of difference between high strength and high performance concrete. That is my point of contention.
Yes, yes, sir. Yes. High strength is when we are talking about performance, you are talking about so many properties that could include strength also. That can include strength also. Whereas when we are talking about strength, we are essentially focusing only on the strength parameter. So uh, I need strength for this material, but I don't care whether it is permeable, whether it has moisture ingress, whether it can control, whether it has enough impact resistance. I don't care all those things, but I just want strength. I mean, I want to achieve in the lab when I crush this concrete. All I need is M50 grade concrete. That is probably you're talking more about strength. There are some applications where you need strength, but you may not need properties. Okay, essentially, you may not need, let's say like moisture impermeability or say durability. You're not too much worried about the durability because it's a place where, even if it's not durable, let us say I'm okay if it stays only for 20 years. I don't care if it works for if the structure works for 50 years or 100 years. You have some situations. There are a lot of temporary structures. Essentially, there are a lot of temporary structures that we work on, and sometimes there are structures that are out there. For example, sewer culverts constantly experience, not culverts. When I talk about culverts, don't think that I'm talking about bridge culverts, like sewer drains. For example, we place concrete sewer drains. So these sewer drains are essentially exposed to all sorts of all sorts of deterioration agents. No, I'm not a materials guy, but I don't want to sound like a materials guy. I'm just giving you some examples, and uh, probably there are experts in here who are material experts here, but I'm just telling a simple example for everybody. So there are structures out there in sun and rain which you're not really worried. I mean, if it's a bridge, you may be worried, but if it's a small wall, the failure of the wall doesn't cause any big problems. Say those kind of situations, you don't really worry about the performance. You don't want to invest tons of money on that, like so many so much of money on that. You just want it a strong strength from the sake of a design standpoint, so you may go for high strength concrete. But when you're talking about high performance, we are talking about ultra high performance. It's not just high, ultra high performance. Obviously, the concrete has to take care of so many properties that I spoke in the previous slides. Those are all part of the performance. Performance is not one thing, just strength. Performance is about so many things. Okay. Uh, So the water cement ratio, coming back to, thank you, Dr. Naidu Garu, for keeping those two things like high strength, what is strength and what is performance. Thank you.
Can I
Water
ask,
cement ratio. Yeah.
can I ask one question, please?
Yes, sir. I don't know
The
who.
checkpoint I have here, the density level between no coarse aggregate mix with the coarse aggregate.
Mhm.
Uh, is that coarse aggregate has higher density than the fine aggregate?
Yes,
I
sir.
forgot.
Yes.
Okay. If that is
Yes.
the case, how can
Ah.
you justify the density is more for the no coarse aggregate?
So let me ask you one question. I mean, this is the easiest way to solve this problem, essentially. This is the easiest way to solve this problem. So diamond is considered to be the most dense thing on the earth, essentially. Okay. Obviously, if you bring a bunch of diamonds and build a structure with that, it should technically be the strongest structure in the world, right? But does
Okay.
that happen? How are you going to make a matrix out of concrete, out of diamonds? How do you make a matrix out of diamonds? I'm so in these diamonds, you put a set of other things, all other things, okay, all other things to make a matrix. So matrix in the sense like grout, mortar, what we call in America they call grout, in India we call mortar. So you're making a mortar. You're making the homogeneity comes from similar size materials. The homogeneity. Why are nano? We're talking about nano cements, nano concretes these days, right? Why are nanoparticles more denser than something that is made of nanoparticles is more denser than something that is made of stone, big stone, granite stone, very strong. Because what matters is not the density of the individual component. We need to realize that. What is the density of water? Density of water. Specific gravity of stone is three times water. Three times. So the aggregate stone, granite is three times heavier than denser than water, right? If you put a granite stone in water, the water it goes to the bottom of the tank in a moment, in a second. It's so much denser than water. But what brings homogeneity to the mix? The water brings the homogeneity to the mix. Common size, commonalities. This is like this is to say that a team of ants are stronger than one lion, basically. A team of ants is stronger than a lion, basically. It's that exactly the same thing. What matters is how the things work together, not the strength of an individual component. We need to know it's not the strength of a component. Nanoparticles
No, I'm not
literally
talking
has.
about the strength. I'm
Uh,
talking about only the density level
mhm,
uh, between no coarse aggregate with
mhm.
respect to coarse aggregate in the mix.
So I can give you. I mean, this is I'm trying to explain the concept previously. Now I'll give you the numbers basically behind this. Okay, so the strength, the densities of mixes, ultra high performance mixes, once they hardened, were reported to be 160 pounds per cubic feet, which is uh, so the we know the regular concrete. I'll tell you in terms of how much it is higher than regular concrete. Okay, 1.07 essentially, 7%. The density in design calculations we cannot take when you are designing ultra high performance concrete. It is suggested to take the density of the concrete, hardened concrete, as 7% higher than, okay, 7% higher than the traditional concrete that is made out of coarse aggregate, fine aggregate, all the things that we know we have been doing for many years already. Okay, the strength of the density of the UHPC with no coarse aggregate, is reported to be 7%, essentially 7% higher than the density of the concretes that use coarse aggregate, fine aggregate, all the traditional concretes. Does that explain your question?
Actually, that's a deviating from my point of question because I am asking only about the density, not the strength.
I'm talking about density, sir, right now. 7% higher density. That's what I'm telling you right now.
Okay.
I'm not telling 7% higher strength. I'm saying 7%. The UHPC concrete has 7% higher density than concrete, traditional concrete mixed design based concrete.
What is the theory behind that?
Right. That's the very important point here. The theory behind that is how good you can pack the materials together. That's what I was talking before that. That's exactly what I was trying to talk before that. Before I gave you the numbers, is how you pack, how you pack a mix that matters.
Maybe my question is stupidity, but
No,
still
no,
I
no.
want.
It's good.
What is
It's
the
fine.
theory?
Yeah, it's very good. Don't. That's a very good question, actually. That's a very good question. The concept is how you are packing the materials together. Okay, the packing is what matters. The temperatures, the interactions between the materials. Okay, one important, very important point is you cannot achieve these densities normally under normal uh, pressure, normal temperature. We all know that. We all know that pressure and temperature matter a lot. If you go back to Robert Boyle's law, Charles' law. Okay, material. There is a strong relation between densities of the materials and the pressures and the temperatures they are subjected to, essentially. So if we compress things under high temperatures, they,
Sir, whatever we compress,
yeah.
the filler material will be either cement or any other filler material, which density will be definitely lower than the granite. So, is it possible to achieve the higher density than the coarse aggregate being used?
Well, I mean, there is one thing, sir. What is the density of cement mortar cubes when you actually test them in the concrete lab?
It may be
Cement mortar.
2200 kg per meter cube.
Cement mortars. So we take cement and sand, just cement and sand, right? Cement mortar mixes. If you see their density, they are very good. They are not bad at all. Their densities are good. They don't have any aggregate piece in that. It's see aggregate is not giving the strength to the mix. We need to change our minds a little bit here. Aggregate is not the one that is giving density to this one. Aggregate, how aggregate? See, density comes from void ratio. To be very scientific, void ratio is the one that is actually, if you have a lot of voids in the mix, your density is going to fall, because the strength of a mix, the strength of a piece is not the strength of the strongest material, but the strength of the weakest joint in a structure, in a chain. The strength of a chain is the strength of the weakest link. The strength of a chain is the strength of the weakest link, not the strongest link. You have stronger, very strong links, and there is one weak link. It's broken. The chain is broken. It's the same way. It's exactly the same way it works here. Okay, you might have diamond piece. You may put a diamond pieces inside your concrete mix, but that doesn't help increase its density by any way. No way it increases the density of the mix, because you have a lot of other pieces. It still breaks at the same strength. It still has the same density, probably lower density, because when you have bigger aggregate pieces, you get more voids around it. I mean, essentially, non-homogeneity in the mix brings a lot of deficiencies in the density. This is where, I mean, in addition to that, how closely you're packing, what are the curing temperatures, and what is happening between these materials when we are curing them, when you are applying heat to these members, when you are, you know, uh, heat treatment, curing with high temperature curing is very essential, which is probably in my, or I was planning to talk a little bit later on that one. Uh, so the interactions, the chemical reactions that happen in silica fume and cement during those high temperature curings, also all these things also change the density of the mix. They impact the density of the mix. So I hope that gives some clarity between what we conventionally have been thinking and what is the change in thinking process. Yes, I mean all the books, MS Shetty, Concrete Technology says, hey, my aggregate is very strong. Aggregate, addition of aggregate is very good for the mix. That's the conventional wisdom. That's the conventional knowledge. You go one step ahead. One
Probably
step.
that depends on the type of aggregate, maybe lightweight or dense weight or something like that. Like
That's
if it,
altogether different, sir. That's another parameter. Like
yeah,
that's
eh,
another parameter, essentially.
given the density of the coarse aggregate, suppose like granite is a more dense than any other. Is it the uniform, the motor, like whatever you say, you don't add the CA with a just mortar like a cement and sand. And is it stronger than the granite mix with mortar?
Can you repeat that, sir? I didn't understand your question properly.
Like mortar, the cement with sand
Hmm.
is denser than the cement, sand, and granite coarse aggregate.
See, that's that question. That thinking is there are a lot of things that need to be that change the equations. That's what I'm trying to say. Uh, so let us say you're putting
What is
two
the
granite blocks inside the
homogeneity?
mix.
What is the homogeneity you are talking about? Only the two materials or more material? More materials.
All the materials in that mix.
So what are the materials you are
Uh,
focusing on?
on the screen, if you see the screen, uh,
Yep.
generally UHPC can have Portland cement, fine sand, silica fume, quartz floor, of course some steel fibers, all these.
Yeah, that because you are mixing the dense material. You
Which
are
material
mixing
is dense
dense
there?
material than the coarse aggregate. So that's
Which
the
one? Which
reason
one
why
is denser than coarse aggregate here?
the coarse aggregate is just like sand, you can say,
Mhm.
more or less just like sand.
I mean, technically, sand is probably kind of similar uh, density as coarse aggregate. If you
Yeah,
get a
yeah,
very good,
that's what I'm
if you
trying
get
to say.
very good consolidation, that's the
Yeah,
part,
that's what I'm trying to say. But
right?
whereas by looking at the other elements,
Hmm.
which are denser than the sand, like the silica fume is more denser.
If you pack it
Okay.
densely, right? If you pack it densely,
Yeah.
if you don't pack it densely, it's not denser at all, right? Like if you take silica fume and pack it very close with no voids in between, then only it's denser than,
Yeah, silica fume itself, it adjusts in the gaps because it's a finer.
right, sir? I mean,
May I,
if you
may I
actually
add something?
put silica fume in the air, it actually kind of floats in the air also, kind of silica fume by itself. If you take a pinch of silica fume and throw it in the air, it probably it just diffuses in the air.
Silica in the micro, like a micro level, if you see with the sand is also the made of silica, but the silica fume is itself is a
Hmm.
micro level than the sand. So that's why it's a denser than mixed with coarse aggregate.
Yeah, I think the original
Because
question was.
I'm trying to my mind to justify whether
Hmm.
it's a denser or not.
No,
May I
I'm
add
again.
something here?
Yeah, yes, sir.
May I add something here? I'm Prasad. May I add something here?
Yes, sir. Please go ahead.
Right. We're actually going for M60 mix and all for a 26-story structure in Hyderabad. Where when we are going for a M60 mix, we are using GGBS, ground granulated blast
Landed
slag, which
blast
is a
furnace slag.
silica fume pipe.
Right.
And then the coarse aggregate is hardly, sometimes it is even lesser than the fine aggregate. But then the
Yeah.
concrete density, the cement quantity also increases to
Right.
about 450 kg per cubic meter. to answer to the question that he is raising, that when you are decreasing the volume of the coarse aggregate, are we getting the density higher than this or not? While we are packing up with the GGBS to an extent of about 30 to 40%, okay, and then the cement quantity, cement and GGBS together equivalent about 450 kg per cubic meter, and fine aggregate, and coarse aggregate is equivalent to fine aggregate sometimes, or even lesser than fine aggregate. We are what we are targeting M60 concrete, we are even getting M70 like that. Okay, it is fine. But then the density what we are talking about is we are always getting higher than 2500, 2550 kg per cubic meter, something like that we are getting. So
Right.
by reducing the coarse aggregate quantity even to 50, less than 50%, we are still getting higher. As the
Right.
speaker is rightly telling about, it is becoming denser. With the
Right.
GGBS addition and all, it is becoming denser. That's why
Right.
we are getting that very densified concrete. Thank you.
Right. It's
Thank you.
the key point. The key point here is, Andy, it's not the single material that matters. It's not the density of the single constituent material that matters. It's how well they blend together. How well they blend together and make the matrix. See, you're getting density when the matrix has least voids. Least voids. That's what gives the density to an object. That's what
Yeah.
gives density to something. So in this case, what Mr. Prasad Garu said just now, you are absolutely right. The same, they tested it in the labs several times. They tested it. They were trying to understand why I am getting better strength or even better density, excluding. I told you again and again, UHPC mixes that were excluding coarse aggregate completely, zero coarse aggregate, were achieving higher densities, lot higher densities. For even for the design purpose, we don't take 2500. We take for UHPC. To put it in perspective, I'll give you what is the exact. I'm calculating. Okay, right now 2,500 into 1.1. We use 2,700 for UHPC for density care for in the weight calculations. When you're actually designing the structure, we don't use 2,500 as the kilograms per cubic meter as the weights for the self weight of the structure. We take 2,700. 2,700.
Just to give you some more information, we sometimes use self-compacted concrete. Okay. For this self-compacted concrete, the densities are always between 2,600 to 2,700 kg per cubic meter. That is the density we get because the cement quantity being higher, and viscosity modifiers will be added. Okay,
Right.
and it will be pumpable, and the density also will be higher.
Yeah.
Okay?
Yeah.
Right. Proceed. Thank you.
Yeah. I mean, those are the standard deviation. I mean, there's always a standard deviation when you're uh, telling the numbers. So when you are actually designing, UHPC might get 2,800 also, but we don't quote
Yes.
that because it's a standard deviation always involved,
Correct.
essentially,
Correct.
in a mix. So you might get, in your case, when you're using self-compacted, sometimes you might get 2,500, sometimes you might get 2,650, 2,700 also. It's possible, definitely. But there is a standard deviation, so we don't quote the numbers, including the standard deviation. We generally quote the ones that are more commonly seen, the average value kind of thing. Yeah.
Can I add one my doubt regarding suppose the aggregate we were talking about. Suppose I'm in Australia. We are using a basalt, the coarse aggregate, which is more dense than any other available, like a granite, whatever it is. It's 3, specific gravity is 3. So is it, if I add coarse aggregate into that mixture, what do you suggest? Whether the homogeneous is better than without adding basalt coarse aggregate?
Definitely, that's what the literature is saying. That's what the people who tested it are saying.
What is the density of your without coarse aggregate you are achieving right now?
They are saying 2,700 kilograms per cubic meter is the normal density.
So my basalt is 3.
No, I'm not talking about the any specific one ingredient. I'm talking about the concrete density.
If I add basalt, that will
Mhm.
be more than 2700. That's what I'm saying.
I don't think so, but I mean, if you think so, we can definitely do a testing in the lab. Do that testing and tell
You
us.
can
Oh,
definitely you can definitely get more than 2700. That's what I'm saying, because my basalt is 3.
mhm,
That means 30.
mhm.
So
We
it's
are will be interested in seeing that.
30 is more than 27. If you take it average 27 plus 30, it should be more than 27.
I cannot comment on that, sir. We'll be happy to see that actually. If we can,
In Australia, with
yeah.
the most aggregate, coarse aggregate is basalt.
Mhm.
The more heavier than any other concrete.
I mean, that doesn't mean the concrete will be high density. No way. It doesn't mean that. It doesn't have to be. That's what I'm trying to tell.
No, it is. It is because we have the Boral manufacturing company here in Australia. They are
Mhm.
manufacturing lightweight concrete and the heaviest concrete with the basalt. You cannot say the homogen is the densest material. That's what I am saying.
Yeah. Okay.
You
I
can
mean,
refer to
you
basalt.
can share that if you have a research
Refer to
report on that.
Boral concrete. They manufactured the heaviest concrete than any others in the universe.
Mhm. That would be interesting to see that.
Yeah, because in Australia, it's a basalt is the very heaviest concrete.
Mhm.
That is
Yeah.
used. That is used for industrial heaviest building foundation structures.
Hello. Hello.
Yes, please. Somebody is trying to say
Yeah,
something.
I'm Dr. Srimaruthi, sir. I want to add some discussion on this aspect. Can I add it, sir?
Oh yes, sir. Please, please. It's an
Yeah. This is
interaction.
This is Dr. Rao from Kakinada, sir. Yeah.
Yes, sir.
Good evening. Good evening, sir. Regarding the material density is considered, it is constituting of mainly two parameters. One is the specific gravity of the constituents. Second one is the void ratio that was in the total matrix, we can say, as a mass. It's a mass density. Finally, it governs the your weight of the structure or the weight of the your final product. In terms of the cementitious products like this, the basic specific gravity of individual components, like we are using some 4 or 5 different constituent materials, the proportioning of the different specific gravities in proportion to their respective proportions will be generally governed by the total density of the material. Besides that, whenever it is a cementitious product, the cementitious compounds at the end of its hydration plays the important role in giving the density. It's like
Yes.
in the modern
Yes.
days. Yeah, 1 minute, sir. I want to ask. Yes, we'll conclude
Yes.
within
Yes.
half a minute. In the case of cementitious materials, nowadays we are going.
Hello.
Sir,
What is a
your voice
Yes.
is not clear, sir. Sir?
yes, sir? Sir, shall I repeat, sir?
Yes, sir. Yes, sir.
It,
You repeat.
it's clear now, sir.
Yes, sir. Yes, sir. Clear, sir.
Yeah, regarding the density of the materials is considered, the density of the final constituent product is a function of the specific gravity and the your void ratio that was there in the matrix. That is the basic philosophy. When coming to the specific gravity, we are using, in the case of a concrete, we are using a 4 or 5 different types of products like coarse aggregate, fine aggregate, water, cement, and in different proportions. The specific gravity of different proportions according to the proportions will be governed in general as a first phase. In the second phase, being a cementitious material, what is the final hydration product that is filling all the pore spaces and all that as a mechanical packing or the cementitious packing that governs our final density. That's why we are getting the, much more density for the latest concrete mixes, like we are using the blended cements that gives the secondary hydration. That gives you the much more pore refinement than the initial primary hydrolysis of 25% white space to almost 1% white space. That is, we are using almost filling the entire white space with the secondary hydration products. That is the main reason. Besides that, if you are changing the different aggregate material specific gravities, definitely there is a change in the total weight of the or the density of the final product, sir. Like we have the special concrete.
I honor that. Dr. Rao, sir, I honor that.
Yes, sir. Sir. Sir, tell me, sir.
I honor your statement, whatever you
Yes,
said.
sir. Yes, sir. Like one within half an hour I'll conclude it, sir. We are using the special type of concretes like using heavyweight concretes like iron ore. Iron ore has a density of 7.85. Like our conventional sand and quartz aggregate is near about 2.75 or 2.65 or 2.67. Basalt you are saying is near about 3. The proportion of the each individual specific gravity and the constant total proportion, the total matrix that gives the density. Besides that, the hydration products, end of the hydration products, which forms the total void space. That is gives the total density of the products.
That's correct. That's correct. That makes sense.
Marty sir, please continue, sir. It's a very good presentation, sir. Glad to meet you.
It's a good discussion, very good discussion. I mean, I said in the beginning, sir, I like to have interaction more than presentation because.
If you permit me, I have one more some clarification.
Please.
Yes. Regarding the eliminating of the course aggregate, what we have learned from our MTech structural engineering is from my guru, Professor Shashkirao sir. What he told is, especially in the case of ice strength concretes, not only the strength of the aggregate, that is the course aggregate, plays the important role. It is the transition zone between the coarse aggregate and your matrix that plays an important role, that is in the power shear transition zone, which governs the strength of the concrete. So suppose you are minimizing the coarse aggregate, that has some sort of advantage in terms of it minimizes the transition zones, first of all. And the second phase is the what is the flowability or the segregation problems are there, the associated problems of concrete, that will be eliminated with the no aggregate concrete, that is especially coarse aggregate concrete, elimination of the coarse. That is the actually what we learned from our guru sir, Professor Shashkirao sir.
Yeah,
I want to add this, sir. That's.
Thank you very much for adding that. If I remember, a few minutes back when I was talking, I told two things. One is the strength, the density depend on. One statement I gave was the chemical interactions between the ingredients in the mix. These are the exact words I used. I said pressure, temperature do a lot of wonders than what we actually expect. That's the I think I quoted Robert Boyle's law, Charles' law also a few minutes back. That is exactly what Dr. Raugar is saying. The chemical interactions at the end of the hydration process, they change a lot. The pressure, which is actually the curing temperatures that we use. UHPC, we need to cure around 100 degrees centigrade, usually. 100 degrees centigrade, which is kind of boiling point of water. So steam curing, essentially. So you're actually applying that temperature for 48 to 72 hours right after the casting of the member. So you're indirectly applying pressure and temperature treatment to the member. So this pressure and temperature are doing some, along with the chemical interactions, and the chemical interactions themselves change a lot because of the pressure and temperature. For instance, you do UHPC mix and then you cure it at normal temperatures in the curing pond, you are now no way getting even 50% of the strength. You don't even get 50% of the strength. The reason is it's not some physical interaction, it is a chemical interaction happening, and chemical equations are always, every chemical equation in the world is different. When the same chemical equation that is conducted at one temperature, the same chemical equation at different temperature yields different products. Same with the pressures. A chemical equation with certain pressure acts in certain way and different pressure acts certain way. So all these things add a lot, and and then finally, I think I quoted the example of a chain also. I said the weakest link in a chain, the strength of a chain is its weakest link, not the strongest link. I think I told this example exactly to say that, hey, your coarse aggregate may be a diamond. Instead of coarse aggregate, I can bring a diamond, the diamond into my concrete mix. Do you expect the strength of the concrete mix or the density of the concrete mix to be super good? No, because you need those other materials, the joints, the which is Dr. Raugar is referring to as transformation zone, which is essentially the joint or the interface between the coarse aggregate and the surrounding material. That matters a lot. That matters a lot when you're doing non-homogeneous things. When you're doing two particles, one particle small, one particle big, how the interface, how the joint works is very, very essential. If the joint is not filled, you are getting a weaker material, you're getting a less denser material, you're getting non-homogeneous. Non-homogeneity is reduction in density many times, if not every time. Okay, non-homogeneity. Homogeneity, I said the strength of the ants is better than a lion, basically. That's exactly homogeneity. Again,
That is between that is you are talking about the bond between the foreign material with the homogeneous material. Like diamond, whatever you say, that's a foreign material, and with the homogeneous material with the
right,
bonding,
right. I mean, the
bonding.
zones, yeah, the joints, the interfaces, whatever you
Yeah,
call the
that's
transformation.
where the stress concentration play the role.
Yeah, I mean, yes, stress concentration can play the role. That is from a stress strain perspective, from a,
Yeah,
how the forces are transferred when you apply some weight. So when I am sitting on top of a concrete block, it's actually definitely transferred through the matrix. And then, you know, when I mean,
yeah, there are
you get
parameter.
more cracks in a non-homogeneous material. That's the
Yeah,
reason you get more cracks in a non-homogeneous material.
yeah, yeah,
Yes,
I agree with that. Yeah,
exactly. In a homogeneous material, you get less cracks because, you know, for the same reason you just said. But density
yeah.
also, I mean,
The
density is
interface,
also
mainly
similar.
the interface. When we talk about the stress concentration, we have to talk about the interface between the different materials.
Right, right. I mean, obviously, cracks are function of stress. You get cracks in the stress zone, essentially.
Yeah. I agree for that.
Yes. So very good. I mean, I love this interaction honestly because it keeps it from not boring.
Yeah,
I mean, other
definitely. Even the
presentations are
stupid
boring.
question sometimes it is, it creates a lot of thinking.
Yes. And again, like I said in the beginning, subject is bigger than all of us. Everybody here, whoever it is, MIT professor, IIT professor, or the
No,
top
see,
research scientist in the world.
no one is
Right.
Superman in the world.
Exactly. We know something, and then we realize that we don't know something. There is something
Yeah,
that we don't know already here. See, like
knowing something is weaker than don't know something. That's my perspective.
I remember reading MS Shetty when I was a student. I was
Yeah,
reading MS Shetty, and all the knowledge I gained from MS Shetty, all of a sudden when I was reading UHPC, it seemed to be counter of that. Many aspects was looking like the counter of what I was learning in MS Shetty may not be, because the way I was learning, I was looking at it is probably not how Mr. Shetty might have intended to, but maybe I was looking at it incorrectly, or maybe we learned some things new because the research has brought up. Many times research brings new items. You may be one day you may be surprised if there is a theory in reinforced concrete that comes out and says, hey, uh, all my what you call those plane fibers are not perpendicular to the neutral axis. You might the very fundamentals of bending theory, which says those very fundamentals, one day you may be challenged. The
that's
research
a,
may come back and say that's wrong.
that's a well-known fact. That's just an approximation. It's nearly the perpendicular or parallel, whatever it is.
Right.
So it
Yeah.
need not to be 0 degrees or need not to be 90 degrees.
Right.
So
Right. I mean, we
maybe
see that in medical all the time. We see in medical, they
yeah,
say coffee is great for your health. Like 15 years back, they said coffee is good for your health. Now they
yeah.
come back and say coffee is not good for your health. They say canola oil is good, peanut oil is not good, and now they're coming back and saying peanut oil is better than canola oil. So it's evolves. I mean, research evolves. They
So
tested.
see at
Yeah.
the bottom line, these are the numbers always, these are the average numbers. They need not to be exactly the same to every person. Like diabetes, see
Yes.
100, the 100 is the limit. No, for my case, it is 105. And
You brought another point, sir. Important point.
it is 90.
Uh,
So that's an average 100. The doctor says, no, yours is 105. Don't depend on the average figure.
Right. Interesting. I mean, you brought very important point. When you can I convert that to UHPC, there is
Yeah.
something I need to share with you all. Uh, so the biggest challenge you might be asking, hey, what is the biggest challenge with UHPC when there is so many good things about this? I mean, I haven't covered even like 10% because obviously I wish I am in that room with you all in Kakinada or somewhere so we can talk this for 4 hours or 5 hours in the day, have a lunch, and then continue for some more time. That would be great thing to do actually because these kind of things we cannot talk in even in one day. We would be covering not even 10%. So the important point was they say, so what is this lack of consistency, like Venkatraman just now you are saying, sir, this lack of consistency in results, it's
Yeah.
it's a challenging ultra high performance concrete. Somebody is making it, they're getting 120 m20. Somebody is making it, they're getting 100 m once with the same mix, m70 they get. Some people get m60. Lot of problems, right? And you know, the material variability, the mix variability, the temperature variability, they're struggling. I mean, the world is really struggling how to actually crack the secret of this material. So you see, there are proprietary mixes very few proprietary mixes in the world, uh, that actually UHPC manufacturers who actually mastered this art. They are very few. They are very formula, computer operated, everything, all the mixes. You know, they are struggling. Other people are struggling because I want UHPC with the local materials. I can't buy proprietary in the sense, for clarity to everyone. Proprietary means somebody is making, you have to buy from them. Okay, like they own the mix. They will never tell you what is the mix design. They just sell it. You are making a building or bridge. You just bring that concrete. You order it. They deliver it. You don't know how they are making it. You have no idea about mix, the proportions, the procedures, how they are curing, all that. But they say, hey, we promise you will get M100 or M120 or M130, something. We just promise it. That's called a proprietary mix. The problem with proprietary mixes is they are very expensive. So because you can't do it with your local materials. If you try to do it, we are
because
not
we
able
are
to
doing
execute.
in the laboratory conditions, so that may not be exactly the similar in
Yes,
the
yes,
field.
yes, sir. That's the number one reason.
When I was doing my MTech, the Dr. Shashkir Rao has given us a challenge that you prepare a mix with 100 with the local material.
Yes.
We have a small group. We achieved it. We don't ask how, because we have exactly followed the theory,
Hmm.
more or less.
Hmm.
So we got exactly the 99, 98 or something like that. We have got we achieved the target.
Hmm. Yes.
So someone say, how you do it? Because it's completely in laboratory conditions.
Yes.
I'm
And
not
that was traditional concrete.
giving any guarantee on the field.
Right. Right. That was even with traditional concrete. We have target strength. We are designing for target strength, which takes care of the standard deviations that happen a lot of times.
Yeah.
And you know, like you said, so because there is so much variability, and imagine what is the case with UHPC, which is completely different. You know, different mixing, different temperatures, curing temperature. I tried in one of the labs in Siddhartha Engineering College. We didn't get it. We didn't get it at all. I don't know. I mean, I was sitting here. I asked the students to do that. Uh, I don't know how sincerely they did it. We didn't even get half of it, honestly, in the lab. I mean, there are a
Yeah.
lot of problems. This is exactly because when you are actually manufacturing this concrete, you can't assume that, we cannot assume that everybody involved has the same knowledge of the impact of what they are doing. So, hey, if I do this way,
And
how is
also
it going to impact it?
environment. We cannot guarantee the same environment.
No way. Yes,
Yeah.
that's right. Yes, sir.
Like
So it's
sometimes
challenging.
in summer we have got some other result. In winter we will get some other result. The water and no, so many parameters. We cannot say stand on one. Finally, the bottom line, I would like to know what is the ultra differentiate between UHPC and HPC.
I think ultra high performance, at least as ACI defines, sir, M ultra high is essentially starting with M125 grade concrete. That's what it defines. Compressive strength of M125.
So it's a strength perspective.
Yeah. The definition itself is from strength perspective.
Okay.
Yes. I mean, of course, it has to meet all other properties also.
That's why I want to mug it up with U is for only strength.
Yes. I think ACI puts it exactly at 22,000 psi as the boundary line. 22,000 psi for mixes with fibers. For mixes without fibers, it is slightly lower. I think 18,000 psi. Without, you can actually achieve without fibers. Also, you can achieve 18,000 psi, which is give me 1 second. I'm struggling between SI units and metric units. 18,000 or
We use
145.
metric. Yeah, we use metric anyway.
Oh yeah, sorry. That 125 is without fibers. Actually, 125 is without fibers. Yes, 125, which is 18,000 psi. I'm using my calculator and telling you.
Okay.
The one with fibers is, I think, 150 M150 essentially starts.
Is that the highest figure in the concrete so far?
Highest, sir. What is that?
Highest strength
Ah.
of the concrete. Is it that 125?
No. That's the lower boundary. These are the
Lower.
definitions of lower boundaries for UHPC.
Okay.
Yes, lower boundary. Otherwise, it becomes high performance. Probably high performance.
Okay,
Not
what
high.
is the nominal highest?
I don't know. I mean, there is nothing that I know. Definitely. No.
Like Euro standards has much more than that, or with the PA, like because we used to use the Euro standards when I was in India, like mixed designs, because Indian standards don't have the more than 60 at that time.
I mean, ACI is definitely behind. America is behind in UHPC. They are not ahead really as much.
Okay.
Everything ACI is referring to. I read ACI 239. ACI 239 or is the book that talks about ultra high performance concrete completely. ACI 239, 239. That's the manual. Okay. So, and in that book, they are constantly referring to research from Europe only, everywhere, especially from the French labs and from Germany, a lot.
I don't know how the buggers they get the high strength concrete than any others. I'm really wondering about, because in India they have so many research labs, they didn't achieve it. Even in America they have.
Sanctity of procedures, sir. The
Yeah.
difference is, I realized is sanctity in the procedure. How well you follow the procedure documented in the book. When I was asking students at Siddhartha, my students at Siddhartha, they didn't follow the things I was telling them. Many procedures they were. See, the materials are not the important part. I repeated, the materials are not the part. The material mix, sir. They say I added the exact mix. No, it's not enough. No way. The temperature, the pressure, the chemical interactions, everything is coming out of the procedure. Every step in the procedure has to be very sanctifiedly followed. Otherwise, you won't get it. You won't get otherwise.
It's very interesting.
Yes. It's a lot of.
After a long time, actually, I forgot the subject. Actually,
I
be honest.
Sorry. I think I didn't even cover 50% of this presentation actually. If you permit me, I'll just very quickly go. I don't talk much into the slides, but I will
Yeah.
just.
Okay, go ahead. Sorry for the interruption.
People will curse me. People will curse me. This guy didn't even talk fully anything. So, yeah, 2% fibers, people. I mean, please, around 2% fibers is what many books typically refer. 2% of the volume of the mix. Okay, is something suggested. Then this is one UHPC mix, proprietary mix actually. if you see the bottom of the screen, can you all see my screen?
Yeah. Can you
This is
please
this.
send me in the PDF the presentation?
Yes, sir. I already forwarded it to our host, and
Okay, I will
he
get
can.
I do.
Please feel free to share with everybody, sir.
Yeah. Okay. Thank you.
So that's a, you see this one. In this one again, I don't see a. This is ductile. Ductile is actually the proprietary mix of a mix that is supplier for Federal Highway Administration in the United States. Federal Highway Administration is like our National Highway Administration, who builds the bridges and highways in the United States. So they actually, when they want to do a UHPC construct using UHPC, they use ductile concrete. The supplier, ductile is the supplier. They supply UHPC to federal highway projects, national highway projects for building UHPC bridges. And I don't see coarse aggregate here. This is the mix actually from their book. Portland cement 28%, fine sand 40%, silica fume 9%, ground quartz 8%. I was Ramana garu, I was struggling. I told our college students, guys, you need ground quartz or quartz flour. They never got it. They were getting some sand, and they were saying, sir, can I use this sand? Can I use this material? I told them, guys, if you use that, you won't get the strength. And they used it without telling me. They never got the strength. These little things, those little things like ground quartz 8%, that matters a lot. If you assume that you can remove that, okay, go ahead, but you won't get any of the properties after that.
Yeah, definitely, because quartz is a high. That's the main ingredient actually in the micro level.
HRW, or high rate water reducing admixture 1%.
That not only fills the voids, that gives the lot of strength, the quartz.
Yes, and it should be ground quartz, so it should be finely ground. Yes,
it's like a silica fume.
Kind of, yes, size of that. Yeah.
Because
an accelerator steel fire at 6% by weight in this mix.
Yeah,
water
it sneaks through the gaps and then fills it and gives the more strength than the sand.
Yes. Then this is another mix from U.S. Army Corps of Engineers. Probably some of you may have known Core Turf is the other proprietary product supplied by for U.S. Army Corps of Engineers. U.S. Army Corps of Engineers build some important structures in U.S. public structures, so they use this mix.
Oh my God! Water is 0.208.
Yes, sir. Yes.
20%.
We can't assume we can actually make concrete with lot less water, right? All these days, we never expected. Yeah. That's in the beginning of this presentation. I was telling, please don't let your conventional thoughts, your conventional wisdom, don't let it block your new perspective.
Yeah.
This is what exactly I was talking. I was shocked when I saw these proportions. I was shocked literally when I saw this proportion first time.
Because silica itself, it is a very, very lubricant within the pores. So that's the reason why I think it replaces the water actually.
Okay, I didn't know that, sir. I didn't know that.
Because silica is a very polished surface, so that's the reason why it's a more lubricant within the gaps of the particles.
Besides that, it is in the amorphous form, sir.
Yeah, glassy structure.
Yeah, glassy amorphous form, highly amorphous.
Yeah, glassy structure. So that's glassy.
Highly amorphous form.
Glassy streak, some whatever, then geology streak or something like that.
Like powdery, kind of powder, like essentially. So this is also important. This when we yes, sir. Sorry, please go ahead, please.
Shall we keep the interaction at the end of the presentation, sir? The time is our.
It's fine. I mean, if we don't have to finish the presentation. I honestly feel the interaction is more important than the presentation.
Oh, sir. Right, sir. Carry on, sir.
Again, I'm trying to be non-conventional. I know I'm trying to be non-conventional. It's okay because you can share the PPT with everybody. They can read the PPT themselves also. Many of
Right,
us.
sir. Carry on, sir.
So the I don't want to stop the interaction. I feel it more useful.
Right, sir. Carry on, sir. Please, sir. Please. Right.
One
so
more advantage of this ultra high performance concrete, especially with the addition of V.R.Siddhartha, we can use it much at a great advantage in pre-structured concrete structures, where we are thinking of getting a very high shear strength. The moment
Yes.
the shear strength is Newton per mm square, I've recently seen somebody constructing a structure utilizing shear strength, increasing it to about 10 Newton per mm square. When you increase your shear strength of concrete to 10 Newton per mm square, then what happens is your crack width and all that reduces also. Okay. Usually we are restricting the crack width to about 0.2 mm in pre-stressed concrete. That gets this high shear strength will make us go for a slim section with a reduced crack width. Okay. There is one more advantage.
Is this Mr. Prasad Garu? Is that you are talking?
Yeah.
Thank you, Prasad Garu. You gave me an opportunity to skip to that slide. Actually, now I'm going to that slide because of you. So,
go ahead.
I can just quickly go there. That is the most important part of actually the most important advantage from a designer standpoint, from an engineering standpoint, really. So this I would talk a little bit about this slide before I go into. Okay, I want to talk about this slide. Very important slide. You see, the blue line is UHPC load deflection curve when tested. When the specimens are tested, the concrete specimens are tested under UTM. Okay, the blue line is the UHPC. The red one is the red one, the tiny, it's small. How small it is? See, conventional concrete. Okay, so see, I mean, there are many things we can talk a day on this curve. One day on this curve alone, we all can talk one day just on this one page, essentially. But I want to quickly do that, so we don't have time because here, see where the first crack is coming. Where the first crack is coming compared to where it is coming in conventional concrete, the tip of the red line, and see how conventional concrete is dropping right after your first crack, okay, which is cracking. It's an, remember, this is unreinforced specimen, concrete specimen tested for compression strength in UTM. Okay, you will you see these things actually in UHPC. You are actually seeing. Do you guys, when you see this, do you guys do the people here? I'm sorry, I'm talking slang. Do you see something that looks like this in the past? Any material that exhibits this kind of curve?
Yeah, it's mild steel.
Yes, excellent. Yes,
mild steel.
Yes, very correct. Mild steel. That means it's such a revealing, shockingly revealing thing that a concrete specimen, which we have been, is actually behaving like a steel.
Yeah,
right?
Mimicking steel. Yes, up to
Yes.
plastic limit.
Yes, sir. That is the most important, very, very, very exceptionally, it's a shocking thing for me when I saw this curve. It's shocking completely because we are used to this on the bottom. When we test concrete, the moment you get a crack in the UTM, that's it, boom, it comes back. No more, nothing after that. It's boom, it's over. We take it out from the specimen.
That means we can, indiscriminately use the concrete along with the steel.
Yeah, I mean, the biggest revelation of this is,
Yeah.
can this replace steel completely?
Yeah.
Can this replace steel completely? Do we need, coming back to Mr. Prasad Garu's point, do we even need steel? And I'm going to answer that in the next few slides.
Yeah, with minimum percentage of steel, we can able to design it, sir.
Yeah, I mean, yes, I mean, Rao Garu, you're right. I mean, how much is that minimum? And again, what is that minimum for? Is it like, if you are designing uncracked structure, essentially, say, okay, so you're keeping the stresses, you are designing the member such that you are designing the geometry of the member, so you're making a beam deep enough that there is no tension developed at the bottom. Technically, you don't need steel here. You don't need steel, right? If you're designing a member to be within the cracking all its life, it's not never cracking. You technically don't need steel in that one. We provide steel because one thing is, even in uncracked structures, we provide minimum steel. Our code book specify minimum steel because we don't want the structure to collapse suddenly if the load goes beyond what we are expecting in our calculations. If we are loading this member with something more than what we are supposed to load it, which is not in our control, the engineer's control or somebody's control, the real structure may be loaded, and then we don't want it to collapse suddenly, crack it and collapse suddenly. So we put minimum steel inside that. Right. Yes. So
that's the way the steel plays important role, because you don't get the sudden failure.
right. In case of UHPC, that tension limit itself is taken from here. This is, if say this is the tension limit in conventional concrete, we are taking it like 2 times higher, essentially 2 to 3 times higher, the tension limit itself. Because of the biggest advantage of UHPC is not its compressive strength. We've been talking M125, we have been talking M150. It seems fancy, but the real advantage is not coming from the compression, it's coming from the tension strength. The tension strength, because of its tension strength, we need a lot lesser steel to make it ductile. I mean, keep it ductile failure. We need a lot lesser steel. And many times we don't even need steel at all. We don't need steel strands. We don't need mild steel at all. We don't need stirrups actually, because the shear strength of UHPC is much higher than the shear strength of, I mean, we all know that shear strength is close to tension strength almost. In any, for concrete, the shear strength is somewhere close to tension strength or slightly less than that or close to that. So
what about the fire rating?
Sorry?
What about the fire rating of UHPC?
That's a very good question. I will come to that in a minute, sir. Give me Venkataraman garu few minutes, sir. We'll come back to that point. So because my idea is people should not curse me here for not going through the very core content. So I'm just trying to complete some core content, which is very important, essentially. Like, how much steel do we need steel or not in the structures? Do we need strands? And then I'll come back to fire rating quickly. Absolutely. Yeah. So that's important point. So here from this curve, you see that one crack cannot fail the member. One crack does not propagate to become a big crack in UHPC. There are a lot of multiple small cracks which do not cause structural failure. And then your strength is actually increasing a little bit to the ultimate from the yield. So it's kind of behaving like a mild steel structure. And then even it's after that also, it's not failing suddenly like conventional concrete. It's actually still exhibiting ductile behavior. The strains, which is the horizontal x-axis, you can see the curve is still going horizontal without just collapsing vertically. That means the member is not actually, after ultimate, even if you don't reinforce, Rao Garu, like you asked the question, after failure, this member is actually not failing instantly like normal concrete. It's actually failing gradually. You're actually seeing ductility here a little bit still.
Sir, what is the ultimate strain, sir? What is the ultimate strain we can expect it?
I think about ultimate strains 0.05 to the range of 0.05. The number is there in the slide after a few slides, sir. I will definitely stop there when we go there.
Fine.
Then, yeah, this I'm not explaining. You can please read this one. These are just different tests conducted on UHPC, comparing with UHPC with FRCs, all that regularly, like conventional concrete. Okay, and you can actually see the strains here, Rao Garu, on this one.
Yeah.
If you see,
yes, I am seeing.
Yeah, so the black one is the conventional concrete. The very tiny black one here is the conventional concrete, and whereas all the ones you are seeing on top are UHPC mixes, different UHPC mixes, like the red line, yellow line, green lines. They are all UHPC mixes. You might see average axial strain, how high it is as compared to simulated conventional concrete. Conventional concrete is so low right here, around between, I guess probably 0.001 is what they got conventional concrete they tested, whereas this one is 0.01, which is probably like 10 times higher than conventional concrete. The strain is, and see the stress levels. Actually, this is this is basically tensile stress. Don't get confused with compression. This is not compressive stress. What they plotted here is tensile stress. That's why If you please focus on the right side of the y-axis, not the left, because the left is KSI, metric imperial units. Metric units. Yeah. The one is FPS, one is SI units. The right side is the SI units. You can see in megapascal, MPa, which is our M. So your conventional concrete is giving you somewhere around 2.8 megapascal, which is M3, 3 Newton per millimeter square of tensile strength at failure, tensile stress. 3 Newton per millimeter square for conventional concrete. For UHPC, we are seeing close to 8, on an average 6 to 9. So say 8 here, 8 or 7. 7 Newton per millimeter square is what we are seeing.
Sir, is
For
it
the
the beam test results, sir? Frictional test results?
Yes. Flexural stress with tensile stress and tensile strain, essentially here plotted, not compression.
Loading. Yeah, 2-point loading, I think so. Yeah.
They call 4 point. Basically, 2 loads at at the shear flexure zones, basically. 1/3 points.
That is point of pure flexion.
Yes. Yeah.
Right.
Pure bending to simulate pure bending in the midspan. Yes.
Right. Proceed.
Yes. Then this is another slide talking much more onto that one, understanding the behavior again. You see the material ductility, all that. I'm not spending much time, guys. I know. Sorry. So it's the important conclusions is when we clearly see UHP not only takes much higher average compression until it starts to strain harden, but also exhibits very significant tensile capacity after cracking and remains ductile until cracking stresses are reached.
Excuse me.
Yes, please.
You have this compression test curve.
Compression test curve. Very good question, sir. I don't think I have that slide with me actually. See, I don't think that I have that slide. They didn't. I didn't get that. Maybe this. Yeah.
This is flexural.
Yeah, this is flexural stress and deflection, not compression. Yeah.
It's okay, sir. It's okay.
I'll send you if I find that plot.
No
sir.
problem.
In my literature, if I find it, I'll send you over. I have written a paper on this one. I'll look at the paper also. That is much more detailed actually. I have a research paper that on this one. I'll definitely send because yeah.
There are a few questions in chat box also, sir.
One moment before I just want to see. Yeah, this is I think Dr. Rao Garu, you asked a question on what is the micro strain levels because of shrinkage related. Compressive strength, conventional concrete. There are comparisons. Tensile strength is what I would put most of the emphasis, and Young's modulus also. Obviously, the modulus of elasticity also pretty high as compared to conventional concrete. These values it's tough to find somewhere for the design purposes really. Traditionally, you can probably have tensile stress before cracking, which is the most important part of a design to decide how much steel goes into the structure, which Mr. Prasad Garu, you were asking. Mr. Prasad Garu, you were asking some time back. So how do you decide? Take it like approximately 2 to 2.5 times. Your tensile stress before cracking is 2 to 2.5 times more than conventional concrete, essentially. So in conventional concrete, probably 600 psi, which is, give me 1 second. 600 psi is how many Newton per millimeter square? 600 divided by 145. You get around 4 Newton per millimeter square, approximately. The tensile stress in concrete, permissible tension in concrete is 4 Newton per millimeter square, approximately.
Point here.
Yeah.
Given that the tensile strength, we can use UHPC for more slender than the traditional HPC, like tensile strength for the UHPC is more than the high performance concrete.
Yeah, definitely it will be higher, obviously.
So that's the mean. We can have more slender members than the when we design with HPC.
Yes, yes, sir.
Okay, that's
Yes,
about
absolutely.
that's the bottom line. I want.
Because where is slenderness coming from? Slenderness is coming from how much allowable tension can be at the
Yeah,
bottom.
yeah,
Because stress is deflections, two things, deflections and your stress or the govern your slenderness, member slenderness, how slender you can design a member. So
yeah,
basically, so the Young's modulus of concrete is a function of compression strength.
yeah.
If you know the compression strength of a member, there's a straight equation for Young's modulus. In IS, it is 57,000 square root F prime, square root F prime C or FSC, what we call FCK. I think in IS we call FCK. In US we call F prime C. So 57,000, because that means compression strength, the most beautiful thing about compression strength is all our formulas, our tensile strength formula, our Young's modulus formula, they are all directly related to our compression strength. So when you are getting higher compression strength, obviously your shear strength, your tensile strength, your Young's modulus, everything is going up. It's a directly proportional to, they are all directly proportional to FCK, essentially, as per our formulas. So when your Young's modulus is higher, because your compression strength is higher, your Young's modulus is higher. Because Young's modulus is higher, your deflections are less. That means for the same deflection, you get a lot slender member. Simple. That's
So the safe limits of secondary deflections will be more than the conventional HPC.
yes, yes, absolutely,
Yeah. Okay.
absolutely, yes.
It also depends upon the creep quotient also, sir. Besides the Young's modulus, it depends upon the creep quotient.
Oh yeah. Creep, long-term effects have to be considered.
Yeah.
Obviously, sir, creep is also a function of Young's modulus again.
Yes,
Very
it's
interesting.
function of yeah.
Exactly, because when your Young's modulus is high, your creep is also your susceptibility of creep goes, obviously goes down a lot.
Yeah,
It's
E by 1 plus
high.
theta.
Exactly. Because Young's modulus, it's a good property. Young's modulus is a great property. Having high value is always easy, good for the structure. So when you have high Young's modulus, your future creep, which is creep is essentially a future thing.
Yeah,
How much creep can happen in the life of a structure also comes down a lot.
Yes.
So your long-term deflections also will be less, essentially, because
Yes.
of that.
Sir,
And then
Babu Mahesh has a bunch of questions, sir, in chat box.
Babu, you can call me, man. You can call me anytime to discuss all these questions. People are waiting here, Babu. We don't have to follow a formula.
No. So we need to know everyone.
Sir, can I have a small last question from me?
Yes, sir.
It's not going to ask the questions, sir. We have the questions.
Only
Yes,
one small doubt. You have shown that flexural curve.
Yeah.
You did not show the tension curve also. Is it available or is it only the?
This is tension curve, sir. Which one is tension curve?
Acha. This itself you said. Okay.
Yes.
Okay. Fine.
This is average axial stress. They didn't mention tension here, but this is tensile stress. If you see the
Fine. I think you
vertical
said
axis on the right side, this is tensile. This is flexural. Where is that? Sorry. Somewhere else. Flexural. Yeah, this is flexural stresses. Stress deflection stress to flexural stresses. If I find compression, I'll send that definitely.
Okay, fine, sir. I think it is quite informative because it is going to be a new material and we all have to, learn this thing. Otherwise, we will not be having any, alternative for the future. We will be thrown out of the field otherwise if we don't learn it. So it is good that Kakinada Center has chosen this topic. I am really thankful to this Sundara Rao as well as the secretary. Thank you very much. Please share the PPT to our Bangalore Center, sir. I will be happy to go through it once again.
Yeah, before I didn't cover all the slides. I'm very sorry I didn't cover all the slides because I don't like a boring presentation, one-way presentation. I never liked it as myself listening, and I don't want to trouble others. This one slide, please see this one slide. This speaks volumes, tons of, which speaks for itself. On the left, you are seeing UHPC member. On the right, you are seeing conventional concrete member. Please focus on the amount of steel that is there. Please focus only on the amount of steel.
Correct.
Yeah.
Do you see that? Prasad Garu, Rao Garu, Ramana Garu, Srikant Chanal Garu, please, it will answer all your questions. This one slide will answer all your questions.
Yeah. I have a last question. Not a question, just a doubt. Have you done any research on composite structure using UHPC?
Using UHPC, I mean, I did not do myself, but I have reviewed a lot of the research done by PCI. Some of my friends professors in Alabama University, Dr. Sri
Yeah, I
Smitharan.
really want to know what is the composite structure using UHPC. What is the performance like? Comparison between the HPC and UHPC. How thin it should be, or how?
Very good question, Ramana Garu. You please see this screen right now.
Yeah.
This is you see the screen. See the right side. Please focus on the right side. The left one is about environment, all those things, life expectancy, those kind of things. On the right, actually, this is done by Dr. Meyer Tadros. He's a professor at Nebraska State University. So he was designing UHPC flanged beam for bridges, and this is the top one is conventional based design. The
I
bottom
can understand.
is ultra high
Just
performance.
like visuals, I can understand what it is.
Yes. You see, if you see, sir,
Yeah.
in the top one in conventional concrete, all those red dots are pre-stressing strands.
Yeah.
60 pre-stressing strands are to be required in the conventional concrete design. Okay. Whereas in ultra high performance, which is the second picture on the right side, option 2.
Yeah.
Okay. He is using 39 strands essentially.
It's
Instead of 60.
almost 40%.
Yes, 40% reduction in steel. And remember, this is heavy reinforcement beam, heavy beam on bridges, very big bridges. This is heavy, massive.
You can economize, 60% steel.
Yes, on and some don't even need any steel. Like if you see this slide, essentially, that one that I showed you a few minutes back, right here, this one right here. You see, there is no steel literally on the left side, VHPC member. On the right side, this member has so much of stirrups, so much of steel, all these things. Then and see the thickness of the web is another interesting part here. Thickness of the web and thickness of the flange. On the top member, the flange is 8 inches. Option 1 conventional concrete 8-inch slab they needed, which is 8 inches of composite slab.
Okay, my next question is, what about the carbonization of the concrete of the UHPC?
Definitely, I would say when you use UHPC, you are producing more carbons, no doubt. You are producing more carbons because you are using a lot of extra cementitious materials, right? Obviously.
No. Exposure to the atmosphere. What would be the carbonization? Like the ordinary concrete will have a very brittle structure after 10 years or 20 years after the exposure. So whereas UHPC, you have any researches for that?
I no, I'm not aware of the research, but my simple common sense tells me that because this is impervious, very highly impermeable material, so chloride ingress is reported to be much lower on this one. Corrosion ingress, because of that corrosion ingress, moisture reported to be very low. Obviously, I'm expecting carbonation also will be very low.
So that means hydrogen embrittlement, whatever it is. I forgot the term. Hydrogen embrittlement will be lesser in the long run.
Yeah, absolutely, because it cannot penetrate the member easily. The penetration becomes difficult. Getting into the core of the member, whether it's moisture, whether it's chloride, whether it's something else, sulfate or carbonation, the material entry into the core matrix and its propagation itself becomes very challenging.
Yeah, because when we go to the bridge inspections with what is it? I forgot sometimes the terminology. We test the concrete. What is?
Hey, somebody asked me a question just now about mixing time of UHPC. Very good question. I could not.
Yeah.
Again, I said it will take like I can we can talk this for months. Lokesh or somebody, sorry, I just saw that popped up on my screen. I want to talk about that one. Mixing time is very challenging for UHPC. Extremely challenging part for UHPC is mixing time. I think who is that? Sorry, who is that? Who asked me? Lokesh. Somebody, Lokesh asked
sir.
that question.
Lokesh, sir, yes, sir.
Yeah, I'm sorry, people. I mean, I may not answer. There may be many good questions here. I'm not even looking at that. I just this one popped up on my screen and I just caught it my attention. I said, Lokesh Garu, yeah, mixing time is very challenging on this one. It's a lot more than traditional concrete mixers. Simple reason: 0.2 water cement ratio, right? 0.2
Sir.
water cement ratio. Simple.
Sir,
That's it. Yeah, it's very challenging.
Sir, two questions I want to, two questions, last questions, sir. Two questions I want to ask.
Yes, sir.
Yeah, regarding the design point of view, is there any standard sustain curves that was suggested in any code for the design point of view?
Not that I'm aware of, honestly.
That speaks a lot, no? So,
yes, there is.
See, I will give you a little information on this. Recently, National Highway Authority of India has about 2 years ago constituted one committee, and then they have seen these ultra high performance test samples and all, and they recently built one good flyover with longer spans in the Maharashtra state. That video also has come in all around. I think ACC people might have also seen that. So National Highway Authority now taking that data, they are thinking of even making a code and all that.
I'm surprised, Prasad Garu, when you said that. Without a code, how did they build a bridge with that?
Right.
First of all,
they have done all the tests required for it.
There
is a big committee constituted for it. There is a big committee constituted for it. How this trunk can be taken, and they have done some preliminary tests on some beams, and then finally they awarded yes, it is good enough to go. And then they have built very longer spans for that. Some video also come. It is already doing rounds all over India.
There are several points. I mean, one thing is there are several points here. I am not sure if they did full UHPC. I wonder. I mean, I doubt actually. I doubt if they did full UHPC based design, beam design, or if they did they used UHPC concrete in some specific specific applications instead of using the beams and designing the complete beams using UHPC. I doubt that really, honestly.
I will send you that particular video.
And because one thing is we don't have a good understanding of that. Number one is we don't even have a good understanding of that, especially in India.
Right,
it's not codified.
Is also built. We can see the data. No issues.
It will be interesting. Could you please share that? Could you please share if you have a report on that?
Yeah. I will send it to Balan Sundarrao. We can circulate it to us.
Right? And I just saw another pop-up from Vinod. Vinod, you're here, Vinod?
Yeah, Maruti. Yeah, I'm listening to you.
Oh, man. He's my another Suratkal batchmate, actually. I'm sorry. I don't see many of you here. I just, something popped up. It said Vinod Viranki. Then I thought, man, he's here. Okay. Good to see you, Vinod. Good to see you. Long time.
Sir, one more question, sir. Yes, sir. Dr. Mathi, sir. Sir, is there any creep behavior studies are available, sir? Being we are constructing with the long span bridges. Yeah, creep behavior is also the real-time behavior is also, but that requires so much of long time for the performance studies. Is there any data is available?
I mean, everything that is related to long term is a challenge on UHPC because it's a new thing, essentially. Because see, to do decent studies on creep, real-time creep studies we are talking about,
yes,
not like
yes, that's
obviously not theoretical study, practical real study. So I mean, you need very long-term data for that one. We don't. There is no long-term data essentially on UHPC structures at all.
Yeah, that's the
because
problem.
Because these are built recently. Whatever is going on, they are built recently. They were not built long back. And even if couple of them are built. They are not enough to, stereotype, right? To make any conclusions, they are not enough usually. So,
is there any failures, sir? Like in the case histories, like using UPHCs?
no, no, sir. There are, first of all, there are few bridges or few buildings or few structures constructed. Number two is, when you're doing these kind of things, you keep a huge margin. Essentially, when you're trying something new, we always keep huge margins, right? Like, uh, so if you're designing a UHPC structure in the college or somewhere, uh, you you don't know how it's going to behave. You don't want it to collapse, so you actually keep some steel, even though it's not required in it. So it's always, no, failure don't happen when you are very, very cautious. Failures don't happen at all. Yeah, I know, not that I'm aware of. I don't see any failures at all. I mean, first of all, very few are constructed, and those that are constructed did not fail. No.
Yeah. One more thing I want to add it is, whenever there is a absence of code is there, we can rely upon the international codes, or otherwise we can use a particular clause of the IS 456. What it says is, it should be based upon the design assisted by testing method. Suppose if you have
Yes.
any experimental data, we can use that
Yes.
experimental data for the design point of view. That provision is there, sir. In our
Absolutely.
IS
I mean,
456.
when we design using this, even normal traditional concrete, also many times on public structures, public engineers actually mandate, like for instance, bridges in national highway projects. In all the projects I did, there is at least one span we real tested, at least in the beginning. There's always one span that we real tested, load tested completely, because National Highways Authority or the public engineers, whoever are the public engineers, they don't let us build the bridge forward until we test at least one span with full load on it, load testing. So, even with proven so many years of theory behind it, when we are doing it, obviously when we are doing UHPC, in fact, many people in America are not ready for UHPC. Many engineers, many Department of Transportations, government agencies are not ready for UHPC structures yet. They have so many questions on that one. I can imagine what will happen in India. I can imagine nobody will let you build anything in the next 25 years. No public engineer will let you build anything with UHPC. It will take time. It will take time.
Yeah, that's fair enough, because it doesn't have much history, so that's the reason why I think they have.
Yeah, I mean, exactly, sir. My idea was, please, to everybody who is here, it's going to be eventually, it's going to take over at least, a large portion of our structures. So when you see something, ask a lot of questions technically, but don't be closed in your mindset to this new material or this new engineering material or its applications to structural engineering. Don't completely shut down. You don't want to construct it, but at the same time, be open to the idea. Do not go for construction until we know everything about it. It's, we are satisfied with the answers we have from the engineers, from the researchers, but don't be closed in your mindset. Hey, I'm not going to do that. Please be open to this idea. That's all I meant to say.
At least because this UHPC is useful for at least residential structures. I'm not going for the commercial structures with a very high rise building, because this is safe enough up to G+4 building, G+4 or something like that.
Yes.
So it's very.
Yeah. I need to I think conclude this call. I have a chess tournament for my son. I am getting very late. Actually, I'm half an hour late already. Just ran longer. Same with all of you, probably. I'm very sorry if it took a lot of time. Sorry for all of you.
No problem, sir. Yes, sir. I would like to read vote of thanks. 1 minute, sir. I would like to thank ACCI Bangalore for the support in this program organization. I would like to thank our center chairman for giving me the opportunity to organize the program, and our Kakinada members for the participation in this program. My sincere thanks to Babu Mahesh for initiating the topic and mobilizing the speaker. My heartfelt thanks to our today's speaker, Dr. Srimaruthi Garu, for his good heart in sharing his knowledge with our members. My thanks to Srikanth Bangalore chairman. My thanks to Sunit, our member, Kakinada, for his valuable support. Thank you, sir. Thank you all. Thank you very much.
Thank you, everyone. Thank you.
Thank you for your time.
Thank you. Thank you very much. Thank you, Dr. Marthi Garu.
Thank you, Andy. Thank you, everybody. Thank you.
అదే కొట్టుకుంది నాన్న